Hello. Hello. Good morning to everybody. Can you hear me? Hello. Once again. Hello. Can you hear me? Hello. Hello. Good morning to everybody. Now this is Srinivas Rao, functional MSc Mathematics, PG second year, sixth paper functional analysis class. Now this is the last session, wave of the online class. Now let us continue. We will discuss the previous class. Now that is closed graph theorem. Just you have to see and refer here. Hello. Can you hear me? Hello? Hello? Hello, okay. Now, just you have to see here. Now, this is 8th unit closure graph theorem. Today, we will discuss the one of the important content. This is also one of the important theorem in the final examination. That is the graph of linear transformation. Okay. Now, what is the graph? It depends upon the linear transformation of this part. A graph of a real valued function f of a real variable x in the pictorial tabulation of the set of all ordered pairs. Now that is ordered pair is that is one of the coordinates x and y. Here x and f of x, where x takes all the values of the domain of the values. Now that's why. Okay. Now, how to define the graph of linear transformation? Suppose let B and B dash two normal linear spaces. Okay. And capital D be a subspace of capital B. Now, here B and B dash, there are two normal linear spaces and capital D be a subspace of the B. Suppose capital T is defined from one of the linear transformation. It varies from D to B dash. Now then the set G of T of ordered pairs. So G of T, G of set is the ordered pair is denoted by X and Tx is there. It is called the G of T means graph of T. It read as graph of T. Now that is the representation of the set of the notation G of T equal to set of X and Tx such that here X being the capital D. Here what is the D? That is the subspace of the Banach space. Now here the graph of T, that is simply it denoted as a G of T equal to set of X and T of X, such that here X being the domain of Banach space of the element. Now clearly here G of T is also a subspace of B cross B dash. Now here B cross B dash means that is the Cartesian components. Now that is the set of all ordered pairs. That is also representation in B cross B dash is here. Now those elements are denoted by x and tx. Here x being the domain and tx is the codomain of the, so that is the image of the part. So here the ordered pair of the element, that is x and tx, that is also a representation of graph of t. So that is the g of t equal to set of x and tx such that here x belongs to domain of the Banach space element. That is the graph definition. Okay, students. Now let us have to see here. Another one, addition and scalar multiplication of elements of G of T. Now what is the addition and scalar multiplication? Already addition of the vector and multiplication of the vector is also there. It depends upon the linear transformation T1 plus T2 of x equal to T1 of x plus T2 of x and alpha T1 of x equal to alpha into T1 of x. But in the replacing of that one, here the graph of the elements here B and B dash, there are two linear spaces. Then by the set B cross B dash, now that is the ordered pair is x and y. Here x being the domain of the Banach space and y being the B dash. Okay, now we define through the ordered pair elements, we must define the addition and the scalar. Addition and scalar multiplication in a B cross and B dash. Now using with the ordered pair elements, that is also here the B of the elements, domain of the elements is x1 and x2, B belongs to capital B, and image of the representation tx1 and tx2. So tx1 means that is the y1, tx2 or t of x2 means that is the y2. So those elements are the image of the elements in the Banach space, that is B dash. Okay, here we are taking x1 and y1, that is the first ordered pair, and x2, y2 is also second ordered pair. Now both elements are belongs to B cross B dash. Now the addition of the ordered pairs is x1 y1 plus x2 y2. So that is x1 plus x2 comma y1 plus y2. That is the ordered pair of the part. Now that is also being B cross B dash. Okay. Now that is alpha of x and y equal to alpha x and alpha y. Here for all x and y is consisting of B cross B dash. Okay. Now that is the one of the ordered pair. Now here alpha being the field of the elements, that is the scalar. Now here we are taking any two Banach spaces B and B dash, define small d on the product space B cross B dash. So small d is also one of the product space B cross B dash as d of that is the product of d of x1 y1 and x2 y2 equal to maximum of now that is the simple representation in between the distance or small d on the product space of the part. Okay. Now d of x1 y1 and x2 y2. So d means that is the metric that is the metric on ordered pairs. That is the maximum of norm x1 minus x2 and norm y1 minus y2. That is the representation of in between. There are two ordered pairs. The difference between the two ordered pairs. Okay. Here x1 x2 being the capital B and y1 y2 being the B dash. Now it shows that the small d is also simple, that is the representation metric on B cross B dash. Okay. Now according to this condition, how to prove the metric M1, M2, M3 conditions are satisfied and at the same time linear space conditions is also satisfied. That means that must be a through the metric elements. Now we must derive the linear space and the normal linear space, and it is on the same manner Banach space is also there through and according to the condition, according to this condition, that is d of x1 y1 x2 y2. Okay, that equals to maximum of norm x1 minus x2 and norm y1 minus y2 is there. Now, what is the closed linear transformation? Now, this is one of the important because according to this condition, we must explain the closed graph theorem. Okay, already graph of t means g of t equal to set of x and tx. Okay, here x being the capital D and tx is also belongs to b dash is there. Let B and B dash, there are two normal linear spaces and here capital D be a subspace of capital B. Now here the linear, define the linear transformation mapping. Define the linear transformation. We are taking here capital D defined T defined from D to B dash. Okay. Now B, that is also a, that linear transformation defined the mapping is also a linear. So then the linear transformation capital T is called closed. If the graph of T is also closed in B cross B dash. When the transformation is closed and linear, now in the same manner, closed if the graph G of T is also closed in B cross B dash. Suppose if convert, you are taking any one of the convergent sequence xn of points of capital D, where here xn converges to x. So here x is already is in capital B is there. That is the domain of the element in the Banach space. So set of txn is a convergent sequence of the basis of B dash. So txn converges to tx. Because xn converges to x, the same manner txn converges to tx. That is the image of the Banach space. Here, when these two conditions are satisfied, one is the x belongs to capital D and the second one y equal to tx. So x belongs to capital D and y equal to tx. When these two conditions are, when the two conditions holds good, then automatically here xn converges to x. When the xn converges to x, so in the similarly txn converges to tx. So that is called a closed linear transformation, means when these two conditions are satisfied through the sequential part, here x being capital D and the second one y equal to tx. When here t defined from D to B dash, that is that mapping is must be a linear and given that linear transformation T is closed. Well, how it is closed? If the graph of T is closed in B cross B dash, then automatically that transformation is also closed. Okay. Now we will discuss. Now we will see the closed graph theorem. Okay. Now just you have to see and refer. This theorem is very important. Okay. Hello. Can you hear me? Okay. Closed graph theorem is let B and B dash. There are two Banach spaces. Suppose T defined from B to B dash be linear. Let capital D be a subspace of capital B and T defined from D to B dash. Then capital T is closed linear transformation from B into B dash. So G of T is also closed subspace of B cross B dash. Now here the statement of closed graph theorem is here there are two Banach spaces. According to their Banach spaces, we must define the transformation of the mapping T defined from D to B dash. Here capital D be a subspace of Banach space. Then given that the transformation is closed linear transformation from B into B dash, if and only if graph is also closed. Graph means G of T is closed. So that is a sufficient part is when the graph is closed in B cross B dash, then automatically the transformation of the mapping linear transformation is also closed. Okay. So that is the statement of closed graph theorem. Now let us see the proof of given this theorem, because here now before the proof of theorem, just we must do it the but we must doing and observe of this proof is here. Okay. Now suppose capital T defined from D to B dash when D is a subspace of B. Suppose capital T is a closed linear transformation. Okay. Now already we know that here G of T equal to set of X and Tx. That is the graph of T such that X belongs to capital D is also a closed subspace. Since already before that capital T is linear, then automatically G of T is also a subspace. Subspace means here already we know that condition. Now that is X alpha plus Y beta is also a subspace condition, or according to this one. Now we show that every point linear and point of G of T belongs to G of T. Now here X and Y is one of the limit point of G of T, which implies that there is a sequence of points, a sequence set of xn and txn in G of T, where xn is also belongs to capital D, such that here xn converges to x and txn converges to t of x. So that graphical G of T is also denoted x and tx is here, and according to that we are taking any one of the sequence xn converges to x. So here the ordered pair xn and txn converges to x and y. Y is also represents tx. Okay. Therefore, xn txn converges to xy is also converges to xn y xn txn minus x and y converges to 0, because that can also be written as norm xn minus x txn minus y. Y means tx or t of tx or y. Okay, is converges to 0. Now that can also be written as norm xn minus x converges to 0, norm txn minus y converges to 0, because according to this one norm condition through the sequential part, xn converges to x and txn converges to y is here. Now since capital T is closed, we have x belongs to capital D and y equal to tx is here. Students, listen carefully. Therefore, the limit point x and y equal to x and tx is also belongs to G of T. So G of T is also closed. See, this is the conversely. Suppose when the G of T is closed subspace, then automatically given the transformation is also a closed through this condition. Okay, just you have to see and observe here. Now that is the main theorem of closed graph theorem, and before this theorem is also it represents the main proof of closed graph theorem is here. Now that is a simple statement of closed graph theorem. So this theorem is very important, and before that theorem is completely depends upon the closed graph theorem main theorem. It depends upon the previous theorem. Now, if B and B dash are Banach spaces, and if capital T is a linear transformation of B into B dash. Then T is continuous. When the transformation is continuous, then automatically graph is also closed. So that is the necessary part. Now through this transformation, when the graph is closed, so given the transformation is continuous, that is the sufficient part. Okay. Now that is the simple statement of closed graph theorem. Students, listen carefully. What is the statement? If a B and a B dash are Banach spaces, if capital T is a linear transformation of capital B into B dash, then T is closed if and only if graph is also T is continuous, the transformation is continuous, we must prove that graph is closed. That is the necessary part. Sufficient part through the transformation, if the graph is closed, closed means g of t equal to, we are taking x and tx. Okay, so then automatically defined transformation is continuous. That is the sufficient part. First, we prove that graph of t is closed. That is the necessary part. Before that, when t is continuous, continuous means now we must be and see and observe the above theorem or previous theorem. Let we are taking one of the ordered pair sequence set of sequence xn and txn. So xn be the sequence and that is also belongs to capital D, or D is also one of the subspace of Banach space. That is the domain of the part, and txn, that is the given the sequence of the ordered first coordinate xn, and according to the image of the sequence txn. So this is also belongs to B dash. So xn and txn be a sequence in the graph g of t such that xn txn convert just to x and y. That is also belongs to B cross B dash. Okay. Now implies, see and observe clearly here. Norm xn txn minus xy. Xy is also converting into at left side. Xn txn minus xy converges to 0. And that is the meaning of norm xn minus x plus norm txn minus y converges to 0 as n tends to infinite. This implies that norm xn minus x converges to 0, norm txn minus y converges to 0 as n tends to infinite. Here, since capital T is continuous, so xn converges to x implies txn converges to tx. So norm txn minus y converges to 0. Norm txn minus y means tx converges to 0 as n tends to infinite. Now, therefore, by uniqueness of the limit, uniqueness of the uniqueness of the limit, we have xy equal to tx. Then automatically graph is also closed. Now that is the necessary part. Okay. Sufficient part is, let us, we will discuss here. Sufficient part, conversely, and first of all, we are taking a graph of t is closed. Now we will show that t is continuous. Continuous means we are taking in the given the linear space, defined the linear space B1, B1 as the linear space capital B with the new norm. New norm means norm x of the new norm is norm x at 1 equal to norm x plus norm tx. So because here just we have to observing the graph t values x and tx, and now we are applying the norm and we are taking the another Banach space is capital B1. We will define the another new norm x at 1 equal to norm x plus norm tx is greater, that is the non-negative part, greater than or equal to 0 for all x belongs to B. And the second one, norm x equal to 0 if and only if norm x plus norm tx equal to 0. Then automatically norm x equal to 0 and norm tx equal to 0 implies if and only if x equal to 0. And third one, now that is the norm alpha x1. Now again we are writing here x1 according to the x1 and x1, we are replacing of the x1 at a new norm x and tx with respect to alpha. Norm alpha x plus norm t alpha x. That is norm alpha x plus norm alpha into tx. Again norm alpha x may be written as mod alpha into norm x plus that is also now mod alpha into norm tx. Now mod alpha is common in this inequality, mod alpha of norm x plus norm tx. norm x plus norm tx means that is the new norm, norm x at 1. Now the triangle inequality, norm x plus y at 1 equal to norm x plus y plus norm t of replacing x by x plus y. Norm x plus y now plus there is a triangle equality norm of in the that is the linear transformation condition, addition of linear transformation, norm t of x plus norm t of y. Now again can also be written as this inequality, norm x plus y less than or equal to norm x plus norm y is here. Okay, now replacing y by tx, we are taking y by here norm x plus norm tx, that is one of the part, and in the x terms in one of the side and y terms is also one of the part. Okay, norm y plus norm ty. So first one is norm x at 1, second one is norm y at 1. So triangle inequality is also satisfied. Now new norm is also a norm on B on the space B1. That is the new norm is also a new norm. We define the new norm that is also a normal linear space part because all the conditions are verified. So therefore B1 at a new norm at 1 is a normal linear space. Again, here the B1 is also another one occurred through the Banach space. We have defined the B1 is here. Then it can be proved that B1 is a complete. Complete means complete normal linear space is called a Banach space. Now, how to prove the B1 is complete? Now, with respect to the new norm, means here we are taking a complete means Cauchy sequence converges. So here xn be any one of the sequence. That sequence Cauchy sequence means xn converges to x and y txn converges to y. Now similarly here the by definition of the new norm, it follows that there are two sequences. Here xn be one of the sequence. Transformation of the sequence is set of txn is here. There are Cauchy sequences in b and b dash respectively. So through this condition, through this one, by the closedness of the graph of t, it follows that y equal to tx. So norm x1 plus, students, listen carefully. Norm xn plus x at 1 equal to norm xn minus x plus norm t of xn minus x. Because replacing xn by, okay, replacing xn plus x at 1 equal to first norm of the sequence, Cauchy sequence, norm xn minus x plus norm txn minus tx. So again, that is also converges to 0. So then automatically B1 is complete. So now observe here, there is a clear observance here, that is norm tx. Now that is the completeness. After the completeness of the bounded is norm tx less than or equal to norm x plus norm tx. So that is the representation of new norm. It follows that t is continuous mapping of b1 into b dash. So here norm ix equal to norm x less than or equal to norm x plus norm tx, because identity mapping is I of x equal to x. According to this one, norm ix equal to norm x less norm x can also be written as norm x plus norm tx. So that is the norm x at 1 through the identity mapping. So here identity is also continuous linear transformation of b1 onto b dash. So in the seventh unit of this part, b1 is homeomorphic to capital B. Homeomorphic to capital B. Therefore, B1 and B both are a whole same topologies. Consequently, given the transformation is continuous on capital B. This is the end of the closed graph theorem. So this is very, very important, students. Don't forget this one. Now, the first theorem and second theorem in this unit, very, very important. If not direct theorem, that must and should be given. First theorem is also given in the final examination. So that is the basement of closed graph theorem. Okay. Okay. Now, just you have to see the self-assessment of this part. That is not necessary. Just you have to see here. Next one, see the inner product space. Please show in the line. Please show in the line. Hello? Please show in the line. Now, this is also one of the important principle of uniform boundedness theorem. Now, this theorem is also called bounded Steinhaus theorem. This theorem is also called bounded Steinhaus theorem. Now, this theorem is also very important. Okay. Now, these theorems are almost all half of the part is completed, and according to the session, entire these 8 online classes. Okay. Now, this is the principle of uniform boundedness theorem is very simple concept. Now the here, what is the principle? Uniform boundedness principle here. Let B be a Banach space and N be a normal linear space over the same scalar field. And let capital A be a subset of B of B and N. The script B represents here the transformation is various from B to N. The set of all bounded linear transformation is denoted by script B of B and N. So here, according to this one, the set of all bounded linear transformation, we are taking any one of the subset is capital A. So that is defined from capital B to N with the property is a set of Tx. So here capital T is also belongs to capital A. That is the bounded subset of N here for here the given the set of Tx such that here T is also one of the transformation given in the subset is there. So you defined the mapping is bounded subset of N for small x belongs to capital B. Then capital A is a bounded subset of script B of B and N. Here defined the subset A is a bounded subset of script B of B and N means the set of all bounded linear transformation. Now this is the statement of principle of uniform boundedness. Now let us see the proof of giving this theorem. That is the simple identification. Already we know that here replacing we are taking the another number of values in the replacing of n equal to 1, 2 and so on, and defined the set is En equal to set of x belongs to capital B. Okay. Now here the x representation of the transformation is norm Tx is less than or equal to n for all t belongs to capital A. Okay. Now here clearly for each n values the set En is a closed subset of capital B. En is one of the closed subset of capital B. Here what is the En? Set of x being the capital B, and through the transformation of the representation norm Tx is less than or equal to n is here. So n representations are 1 and 2 and so on. This is also one of the subset of capital B. By hypothesis we have capital B equal to union of En representation. Union of En, that is the countable infinite. So union of union n equal to 1 to infinity arbitrary union of En, since capital B is complete by Baire category theorem. What is the Baire category theorem? Every please respond here. Hello. Already we have told here every complete metric space is of a second category. So that is the Baire category theorem. And according to this, here there is nowhere done subsets, non-empty interior is there. At least one, that is the existence of the part E n naught. So thus the set E n naught contains a closed sphere is S naught. So already closed, some problems are practiced irrespective of the S of X and epsilon. S naught with center, X naught is be the center and the radius is R naught. So we are taking by the definition of the E n naught, it follows that norm T of Sn, norm T of S naught less than or equal to N naught for all T belongs to capital A. Since x naught belongs to s naught, it follows that Sn naught minus x naught is a closed sphere with origin. Say origin as center and the radius is r naught. So further, here norm T of s naught minus x naught less than or equal to 2n naught. So for all T is also one of the subset of given in the subset of the transformation. T belongs to A. So from this it follows that S naught minus X naught by R naught is the closed unit sphere S. And what is the closed unit sphere? Norm T of S naught minus X naught by R naught. So we are taking on both sides dividing by R naught is here. So T norm T of S naught minus X naught by R naught less than or equal to 2 N naught by R naught. So for all T belongs to capital A. So that is norm T of S less than or equal to 2 N naught by R naught. For all T belongs to A. So now here the boundary condition is this shows that norm T equal to norm means supremum of mod T of X and here R belongs to S. So norm T of S is cannot exceeds 2n naught by R naught. So the given the set is bounded and hence here capital A is bounded subset of script B of B and N. So that is the uniform boundedness theorem. Okay, this theorem is also very important, students. And according to the uniform boundedness, sometimes this is also given. That is, this is the one of the short answer in examination. Suppose these two theorems are clubbed into one of the essay question is given. So that is, let capital A be a subset of a normal linear space N with the property set of f of n such that from x belongs to A is bounded for each f belongs to n star. Then A is bounded subset of n is here. Okay. Now this theorem is also just you have to see and refer. And any subset of the normal linear space, we are taking set of f of n such that from x belongs to A. So given the defined the functional part is also bounded for each f belongs to f is also in the dual of this part. Okay, that is the n star. So given the subset is bounded subset of n. This theorem is also very simple, and this theorem completely depends upon the uniform boundedness theorem. Now, according to the uniform boundedness theorem, set of Fs from x belongs to A is a bounded subset of here Fs of f equal to small f of x. This is the one of the natural embedding of the part. Since the natural embedding preserves norm, so given the subset is bounded subset of n is here. Students, this is one of the important theorem here. Now some other applications through this uniform boundedness. Okay. Now let us see the inner product space. Okay. Please stay on the line. Please stay on the line. Students, let us see here. What is the inner product space? This is very important, especially in the functional analysis and operator theory paper. And before the definition of inner product space simply notated as IPS. Now already we have learned in undergraduation level, and according to that, that is the linear algebraic paper. So through this one, now we have to discuss the some other concepts of in just you have to learn in real analysis paper. That is the MSc first year. Okay. Now in the algebraic concept, so what is the inner product space? So that is simply IPS. Noted as IPS is here. So this is the product relation is here especially. Okay. What is the definition of inner product space? Let X be any one of the vector space over the field K. K be any field is here. So those field elements are scalars. Now those scalars of the elements say the real numbers are complex numbers. Okay. Now here X be any one of the linear space or vector space here. But through the field elements, those field elements are the real numbers. That is called a real linear space. And I must explain thoroughly, especially in this session. In this session means the last previous classes from the beginning of the part, all the field elements are scalars. Those scalars are represented in the given in this field. So the real numbers are complex numbers. So those according to the real numbers must define in the vector linear space, that is called a real linear space. Suppose we are taking the complex numbers, that is the complex linear space. That is also real vector, complex vector spaces. Okay. Now here, first of all, so you have to define the inner product. We are taking the inner product on capital X. That is the function easily part. Okay. Now it is denoted by so product is also lies between, you are taking the product lies between less than and greater than. So inner product means any one of the product, we are taking the product of the function lies between the less than and greater than. That is the representation of the inner product region. So yeah, in the product is also taking the inner region is here. So that's why that is called inner product on X. So here, first of all, so you must define the X cross X on X, X cross X to K such that the following axioms are satisfied. So inner product means IP, space means IPS, inner product space. But here we are taking the inner product of the function, so that is IP1, IP2, IP3. When these three conditions are satisfied, that is called inner product space. First one is the non-negativity condition. So here, when the inner product of X and X, it read as, just you have to see and observe IP1, inner product of X and X. So, like, first up, you must write less than and lies between the less than and greater than. So, we are taking the one of the element inner product of X and X is greater than or equal to 0 for all X belongs to X, and inner product of X and X equal to 0 if and only if X equal to 0. So, here the null 0 means null or 0 vector in X. Second one, here the condition is inequality with respect to the under vector addition. So here x plus y and z. So that is also a distributivity is here. So we can write say inner product of x and z plus inner product of y and z for all x, y, z belongs to capital X. At the same time, inner product of alpha x and y equal to alpha of alpha and inner product of x and y for all x and y is also belongs to capital X. Okay, that is the second condition of inner product. Third condition is conjugacy relation. So conjugate of inner product xy can also be written as inner product of y and x. For all xy belongs to capital X. So here that is a double digit here. Double notation denotes the conjugate on conjugate in K. So bar indicates the conjugates. So conjugate of x and y equal to inner product of y and x. Okay, here just you have to simple one. First one, IP1 in the above definition is positive definite. First one is the positive definiteness, and the second one is called shows the linearity, and third condition means that is the notates. Third one notates conjugacy. Okay, here IP1 is called positive definite. So IP1 is called positive definiteness, and IP2 is called linearity, and IP3 is called conjugate symmetry. So when these three conditions are verified, that is called inner product space. Now, first of all, we are taking define the mapping is inner product of the function. Inner product function defined on x cross x2k is said to be an inner product space. Now these axioms must hold good. First one is IP1. Here the positive definiteness, that is x and x is greater than or equal to 0 for all x belongs to x, and inner product of x and x equal to 0 if and only if x equal to 0. So that is called here, that is also called 0 means null or 0 vector. Okay, that is the IP1. So that property is called positive definiteness. Second one, linearity. So x plus y with respect to z. So inner product of x and z plus inner product of y and z. That is the linearity part. And inner product of alpha x and y equal to alpha of inner product of x and y. That is when these two conditions are verified here, linearity condition also holds good. Third one, conjugate symmetry. So conjugate of x and y. Conjugate means bar. So inner product of the conjugate of inner product x and y equal to inner product of y and x. When these three conditions are satisfied, that is called inner product space. Next one, and yeah, these three conditions are according to these three conditions. We will discuss. There are so many examples. Okay, there are so many examples on inner product space definition. Okay, now that is here one of the important condition here through the inner product following the conditions. Here already we will discuss the IP2 is here. That is the linearity condition. Inner product of x plus y and z. So, but here inner product of x and y plus z equal to conjugacy of y plus z and x. So, conjugate of y and x plus that is also distributes z and x. So, so conjugate of so addition is also the individual of the conjugate symmetries y and x and z and x. So conjugate of y and x by IP3 property is also applied here. That is in the conjugate, that is the inner product of x and y and plus inner product of x and z. Now again, we are applying here x and alpha y equal to conjugate of alpha y and x. So conjugate of alpha of y and x. So alpha bar of conjugate of y and x is here. So conjugate of y and x means x and y. Okay, now this is also when these two conditions are verified in the, so number of times in the short answer is given. There are number of students to blend and present the answer is here especially. Okay, there is the very simple concept of inner product space. Okay, so this is the definition of inner product space. And some other examples, there are so many examples of inner product space here, especially first example. Now it defined on the usual dot product and vector representation, the forces. That is the physical representation is also taking here the angle between these conditions. Now we are taking the in the matrices of this concept. So these examples are also considered in the inner product space. There are so many examples here. Suppose there are. This is the second example. Now consider the set x equal to r power n. So n tuples of the real numbers. We are taking alpha 1, alpha 2 and so on alpha n. These are all real numbers given in this field. So that is called you. Okay, with respect to point wise vector coordinate wise addition and multiplication of real scalars. Here we are taking the alpha means n tuples of the alpha elements, beta means n tuples of the beta elements. So under the vector addition condition is alpha 1 plus beta 1 and alpha 2 and beta plus beta 2, so on alpha n plus beta n. And the next one, lambda of alpha 1, alpha 2, so on alpha n equal to lambda alpha 1, lambda alpha 2, so on lambda alpha n is here. Now we are taking the, in between the, there are two elements, alpha and beta, n tuples of the elements given in the capital X, that lambda being the real number. Lambda being the real number. Now elements of capital X will be denoted by alpha cap equal to here alpha 1, alpha 2, so on, alpha n. So alpha cap means alpha 1, alpha 2, alpha n. Beta means beta 1, beta 2, so on, beta n. So inner product of alpha and beta equal to summation alpha I, beta I. We claim that alpha equals to n tuples of the elements, beta equals to n tuples of the elements. Here, inner product of alpha and alpha equal to 0. If and only if inner product of alpha and alpha means summation alpha I square equal to 0. So if alpha equal to 0, I means 1, 2, and so on. So alpha means 0, 0, so on 0. That is the 0 vector of x. So we are taking in any two elements n tuples of through the n tuples of the elements when the conditions are verified here in the IP1, IP2, IP3 conditions. When these three are satisfied, so that is called given the n tuples of the real numbers. Set of n tuples is also an inner product space. So alpha plus beta, that is IP2, that is the linearity. When the linearity condition verified, alpha plus beta with respect to or gamma is here. So alpha I plus beta I. Now that is we are taking the I representation in the summation of the values, summation alpha I, gamma I plus summation beta I, Ri. So again, inner product of lambda alpha beta equals to lambda of mod lambda into summation alpha I beta is here. So lambda, that value is lambda into summation alpha I beta I is notated as inner product of alpha and beta. That is also a, when these three conditions are verified here, that is called n tuple. The set of n tuples is also an inner product space. That is the one of the example. Now in the same manner, we will discuss the through the n tuples of the complex numbers. There is no doubt. Okay, there are now these examples are considered in inner product space of this part. Okay. Now there are so many examples. The set of all continuous functions on closed interval 0, comma 1. Now this is also well example. See the 10.4.5 because the number of times is given. That is a basic definition of in an inner product space. Define inner product space. Give examples briefly. Any suitable example is on briefly. That is a simple question. Okay, when the already we are taking the we must taking the one of the inner product lies between the less than and greater than. That is one of the defined mapping. Must holds the when these three conditions are verified. That is IP1, IP2, IP3. So inner product of the mapping defined on X cross X2 capital F. Okay, capital K. So that is an inner product space means IP1, that is the positive definiteness. IP2, so that is the second one is the linearity. Linearity means linear. There are two conditions are verified here. Okay, alpha plus beta with respect to gamma equals to inner product of alpha gamma plus inner product of beta gamma. And second one, inner product of lambda alpha gamma equals to lambda into inner product of alpha gamma is here. Now there are we are taking the set of n tuples is also an inner product space through the real numbers and complex numbers. There are these two are suitable examples. Now another one, consider the set x bar equal to closed interval 0, comma 1. That is the representation of complex valued functions defined on closed interval 0, comma 1. Now we are taking any two functions f and g or any two complex valued functions in capital X, and again lambda be the complex number, that is the field of the elements, and lambda f of t equal to lambda into f of t. and according to these values under the vector addition and scalar multiplication, we are applying in a IPS part. So that is IP1, that is the inner product of f and g is greater than or equal to 0, then automatically integral 0 to 1 f of t into g of t bar dt. So according to that, inner product of f and f is greater than or equal to 0. So that is integral 0 to 1 mod f of t whole square dt is greater than or equal to 0. Okay. Now t lies between closed interval 0 comma 1. That is 0 less than or equal to t less than or equal to 1 is here. So that is the positive definite condition. Where in the same manner IP2 is also there. Inner product of f plus g with respect to h equal to inner product of f and h plus inner product of g and h. Okay. Now that is the IP2 condition. In the same manner IP3 condition is also there. Second one is linearity. Third one, conjugate symmetry. So that is the inner product of conjugacy means the f and g bar. That is the bar of inner product of f and g bar equals to through the definition integral 0 to 1 f of t into g of t bar dt, and conjugacy is also applied. Bar is also taken here. Integral 0 to 1. Again, that can also be written as f of t and g of t double bar is here. So g of t double bar means g of t, and f of t bar means a bar f of t is here. So that is by the definition. So that is the value of because t belongs to closed interval 0 comma 1. That value is inner product of g and f. So conjugate of f and g equal to g and f. When these three conditions are verified, then automatically that is called in an inner product space. These examples are well established examples. There is no doubt. See here. There are so many number of examples in inner product space. Okay. Now that is this is your practice purpose. Some other physical appliances is also applied in inner product space. So enter the concept. Now see the Cauchy-Squarch inequality. Now this inequality is very, very important, students. Recently, this theorem is given. Now so many students are should not present as an properly. Okay. Now this theorem is also very important. Now this is also in under UG level is here, undergraduate level. Okay. Now just you have to see and refer the inner product space in UC level, then automatically easy to achieve, especially in this functional analysis. Okay. How to prove the Cauchy's inequality? The examination is given state and prove Cauchy-Squarch inequality or explain Cauchy-Squarch inequality. Now this inequality sometimes this is also called Cauchy-Squarch-Bunkowski inequality is here. Okay. Now this inequality is let inner product space represented X under inner product. It read as X under inner product be an inner product space be an inner product space, then for all x and y belongs to capital X. So in the inner product space, we are taking any two inner product space elements, that is x and y. Okay, that is mod inner product x and y whole square, absolute of inner product x and y whole square less than or equal to, so that is inner product of xx and yy. So inner product of xx means norm x square, and this is norm y square is here. So absolute of x and y whole square less than or equal to inner product of x and x and plus inner product of y and y. This is the Cauchy-Squarch inequality or Cauchy-Squarch-Bunkowski inequality. Now let us see here proof. That is a simple. This is the one considerable part of put y equal to 0 or x equal to 0, whatever it is. The 0 means 0 vector. So inner product of x and y is equal to 0. So then automatically when the LHS is 0, then automatically RHS is also, it is an individual effort of each and everyone is zero. So we are nothing to prove. So as the above inequality, in fact, both sides are equating to zero, then automatically easily to achieve. Okay. Now then assume y not equal to zero. That is the second case. The first case, either y equal to zero or x equal to zero. In the second case, so then automatically LHS 0, RHS 0. So the second case is y non-zero means we are assuming the one of the arbitrary scalar, that is the lambda be the one of the arbitrary scalar. Definition of inner product, we have inner product of x plus lambda y and x plus lambda y is greater than or equal to 0. So x plus lambda y and x plus lambda y means xx, x lambda y and lambda y and x, lambda y and lambda y. So inner product of that again that can also be inner product of x and x plus second part x plus lambda y means lambda bar, because lambda is in the complex coordinate is here. So that's why it denotes the lambda bar of x and y plus in the third part of lambda y and x. So y be the real part, that is the first coordinate. So that's why lambda of y and x plus in the both coordinates are along with the lambda. So that is lambda y, and lambda y means lambda into lambda bar, because complex coordinate is represented by the field element is the scalar. So that is the bar notation. That is the image of the element, imaginary of the element. So you suppose ordered pair of x and y. That is the meaning of x plus iy. Ordered pair of a and b, and bracket of ab means a plus ib. Okay. So b be the second coordinate. That's why you are taking the imaginary of the element z equal to x plus iy. Suppose here lambda y and lambda y means lambda into lambda bar of y and y. So this is x and x plus lambda bar x and y plus lambda of y and x can also be written as the IP3. Conjugate symmetry is also applied here. Conjugate of x and y plus lambda into lambda bar means mod lambda square. That is y and y. So y and y is greater than 0, thus taking lambda equal to inner product of x and y by inner product of y and y. So that is our assumption. Now that value substituting in the above expression x and x plus here lambda bar means x and y bar by xy by yy minus xy by yy of xy bar plus mod xy whole square by mod yy whole square of y and y is greater than or equal to 0. So lambda value substituting in the above inequality, now then automatically easily to achieve in the next one. See the next step. So that value is inner product of x and x minus here mod x and y whole square by y and y minus mod x and y whole square by y and y plus mod x and y whole square by y and y is greater than or equal to 0. So finally, after the cancellation, we are getting here x and y. Enter that value is positive definiteness. So finally, absolute of inner product x and y whole square by inner product of y and y less than or equal to inner product of what is that? Inner product of x and dx. And again, inner product of x and dx. After the cross multiplication, we are getting the here inner product of x and y whole square less than or equal to inner product of x and dx and inner product of y and y. That is the simple notation. Very easiest simplification is here. So norm x means, what is the definition of a norm? Norm x means the square root of x and dx. So then the Cauchy's quad inequality can also be stated as mod inner product x and y. Mod inner product x and y less than or equal to norm x into inner product of x and x can also be written as norm x into norm y. For all x and y belongs to capital X. Because here now in the previous part x and y whole square less than or equal to inner product of x and x and y square is also considered this side. So that is also square root of x and x, square root of y and y. So in the absolute expression is mod x and y whole square less than or equal to inner product of x and x, inner product of y and y. But if not, the square is also in the left side of the square, converting into this side, we are taking in the norm. So norm x and y, mod inner product of x and y less than or equal to square root of x and x means norm x, square root of y and y means norm y. That is also very simple statement. That is the Cauchy-Squarge inequality. In the left-hand side of the absoluteness is also converting into the norm on the right-hand side of this part. Okay. Now, it considered that is also in the same manner. Absolute of inner product of x and y is then equal to norm x into norm y. That is a simple notation. Okay. Now, when the linear dependence of x and y will take for Cauchy-Squarge inequality. Okay. Now, this is also one of the proposition. So that is x under inner product. It read as x under inner product. Be an inner product space. Be an inner product space for x and y belongs to capital X. X and y. So this is just you have to see the proposition. Absolute of inner product of x and y equal to norm x into norm y. It holds if and only if x and y both are linearly dependent. That is the necessary part. Suppose we are taking the x and y both are linearly dependent, we must prove that absolute of inner product x and y equal to norm x into norm y. Now this theorem is also very important. It is completely depends upon the Cauchy-Squarge inequality. Just we will you must refer the 10.5.2 proposition. This representation is also very important. Let us see the proof. This proof is also considered in the above theorem of the same manner. Okay, if y equal to 0 on both sides are whole squared. If y not equal to 0, lambda equal to that is the representation is inner product of x and y by y and y, or inner product of x and y by norm y square. Any value is here. Okay. So first of all, you must find the x minus lambda y and x minus lambda y. So that is x and minus lambda y, and minus lambda y and x, minus of means plus lambda y and lambda y. That is the representation. So after the simplification, we are getting the here norm x square minus norm x square. So that value is also equal to 0 because given the condition is linearly dependent. So conversely, x and y are linearly dependent. We are taking the value x equal to alpha y. Then by the positive definite condition, here we have mod inner product x and y equal to norm x into norm y. Okay, when the norm x equal to square root of x and x is x belongs to capital X. Another proposition. So norm x equal to square root of inner product of x and x. So x be an inner product space. Now prove that double mod of the product defined by norm norm x equal to square root of x and x. That is the simple notion in an inner product space. Okay. Now each and every one is important here, especially. So this is the triangle inequality. Norm x plus y less than or equal to norm x plus norm y. So see this inequality. Norm x and norm y. Here x and y belongs to capital X. So that triangle inequality is norm x plus y whole square. Recently this one is given. So that can also be written as x plus y means z is there. So norm z square means the inner product of z and z, replacing z by x plus y. Now that can also be written as x and x, x and y and x, y and y. So that is the simple concept. So again, here norm x and inner product of that value is norm x square plus and x and y plus conjugate of y and x means conjugate of x and y plus norm y square. So 2 into r plus here x and y representation represented as z. Z plus z bar means 2 real z. Z equal to ordered pair of x and y. Or ordered pair of x and y. So here norm x square plus 2 norm 2 real of x and y plus norm y square. So real of z equal to z plus z bar. So that is the simple concept. So it cannot be exceeds less than or equal to norm x square plus 2 mod inner product of x and y plus norm y square. So by Cauchy's square inequality is also applying in triangle inequality. So mod inner product of x and y less than or equal to norm x into norm y. So entire that value is a square plus 2ab plus b square. A means norm x, B means norm y. So that value is norm x plus norm y whole square. So squaring on taking the positive square root on both sides. Now that is norm of x plus y less than or equal to norm x plus norm y. Now here the inner product is a norm on the inner product space. Now once again I must have to repeat here norm x square equal to inner product of x and dx or norm x equal to square root of inner x and dx. So the above inequality is called triangle inequality is also very important through the definition of an inner product space and Cauchy's square inequality. Okay, and another proposition is here x under inner product to be an inner product space over the field capital K, then the following identity holds good for all x and y belongs to x. Suppose you are taking the any two IP inner product space elements. In case of given the field is real numbers, so inner product of x and y equal to 1 by 4 of x plus y and x plus y minus of x minus y and x minus y. Suppose given the field of complex numbers, inner product of xy means suppose that is the cross multiplication 4 inner product x and y or inner product of x and y equal to 1 by 4. That is inner product of x plus y and x plus y minus x plus y and x minus y plus I of x plus I y and x plus I y minus I of x minus I y and x minus I y. Okay. Now these two conditions are satisfied here. First of all, you must write the given the field of the elements real numbers. That is, those elements are consisting given in an inner product space. Already we know that x plus y norm x plus y is inner product of x plus y and x plus y. So that's why xx, xy, xx, xy and yy. So here x and y equal to conjugate of y and x. Now that is the clear observation here. Now again x minus y and x minus y. Now in the same manner xx and x and minus y and minus y and x minus of minus plus y and y. So x under inner product is a product, real product space. Therefore, y and x can also be written as inner product of x and y. So x plus y and x plus y equal to x minus y and x minus y. So that value is 4 of the substitution of both values 4 into inner product of x and y. So finally, inner product of x and y equal to 4 converting into this side 1 by 4 of x plus y and x plus y minus of x minus y and x minus y. Next one, by the another property is in an inner product space, x plus y and x plus y, after the simplification of, we are getting the xx, xy, conjugate of xy, and inner product of y and y. The same manner, you must, after the simplification, x minus y and x minus y. So that value is also considerable. Third one, I of x plus iy and x plus iy. So I of xx, xiy, iyx, iy and iy bar. Iy and Iy bar. So here, after the simplification, I of xx and x and I is also there. I is considered in the imaginary of the elements. So that is I bar of x and y. Again, here I is the third part is I is the real. So I of y and x plus last one Iy means that is the real is I and imaginary is I bar. I into I bar of y and y. So after the simplification, here I of xx, I bar means minus I of xy plus I of y and x means conjugate symmetry of x and y plus alpha being the I into I bar means mod I square. So I of xx plus xy minus of conjugate of x and y plus I of x and y and y. So after the simplification, we are getting the value is x minus iy, x minus iy. In the same manner, we are getting here. Okay. Now finally, x and y means 1 by 4 of x plus y minus of x minus y by x minus y plus I of x plus iy and x minus iy minus I of x minus iy and x minus iy. So after the simplification, all those values are simplified here. Okay. Finally, here inner product of x and y equal to, so this is the parallelogram law. 1 by 4 of, this is the polarization identity. Identity. So explain the polarization identity with respect to the norm. So inner product of x and y equal to 1 by 4 of x plus y whole square, norm x plus y whole square minus norm x minus y whole square. And inner product of xy equal to already recently that is also proved here 1 by 4 of norm x plus y whole square minus norm x minus y whole square plus 1 by 4 of plus I into norm x plus I by whole square minus norm x minus I by whole square. Okay. Now these properties are verified here. Now these are all self-assignment questions. Now this is also one of the proposition. Let X be an inner product space and X and Y belongs to capital X. Now this the polarization identity is so norm X plus Y whole square plus norm X minus Y whole square equal to. Now all the students are very silliest thing. There are some students are applying in the basic concept a plus b whole square equal to a square plus 2ab plus b square and again a minus b whole square equal to a square minus 2ab plus b square. Those values are adding and we are getting the 2a square plus 2b square, that is 2 of a square plus b square. Now according to this, replacing a by norm x is here. There ends the proof. Replacing a by norm x, that is 2 of norm x plus 2 norm x square plus norm 2 into norm y square. That is a simple expression. Suppose when you must thoroughly practice inner product space and examples and further operators, linear operators, then automatically easily to pass. That is the one of the choice. Okay. Now, here the concept is there ends the part. Okay. Please wait the students. Now, please note down the some other important theorems and problems in the remaining units because time is enough because time to less is here only 15 minutes. Now, if you have any doubt, now this is the last session. So, if you have any doubt, please contact us and personally for the through WhatsApp for the subject point of view. Okay. Now, if you have any doubt, please contact us and personally through WhatsApp is here. Okay. The 11th unit is Hilbert spaces. Please note down Hilbert spaces. Please stay on the line. Now, students, once again, I'm telling here only eight, these classes are eight online classes. Now, these sessions are very much more useful, for, especially in your preparation. Okay, now that's not an ordinary joke because yes, please, a number of times you must watching these classes, these sessions through the YouTube. Now then automatically easy to achieve and answerable in the especially functional analysis paper. Now, functional analysis paper, it is also in the same manner. That is the operator theory. That is the 11th paper. If you are taking the operator theory, then easy to answer. Here, the operator theory paper is here. Okay. Now, the total number of units is 18 here. Now, I think 18 units are here. When you must thoroughly practice in the first 11 units or last 8 units. Now that is the easy to score now out of say 70% of the marks in especially in the functional analysis paper. Okay. Now just we will define the Hilbert space, that is the unit 11. Okay, what is the Hilbert space? What is the Hilbert space? Now, here the consider the inner product C of closed interval 0, comma 1 when the inner product on C of closed interval 0, comma 1 is given by. Now, this is one of the example of especially in this theorem, completion theorem is also here. Now, see this example. Inner product of f and g equal to integral 0 to 1 f of t into g of t bar dt. Now, the set of all continued function in an inner product space. Now, here f and g both are belongs to C of closed interval 0, comma 1. Now, all the inner product space examples is also considered in Hilbert space. Okay. Now, this example is also very important. Just you have to see the definition of Hilbert space. Okay. An inner product space which is a Banach space. Now, when when the inner product space is a Banach space with respect to the norm, that is called a Hilbert space. Very simple concept. So in each and every example, four examples are also considerable the Hilbert space of this part. Through the now those examples are consisting inner product space. That is also same example. Those examples are also preferable in Hilbert space. Okay. Now the definition of Hilbert space is an inner product space which is a Banach space with respect to the norm. That is called a Hilbert space. Okay. This definition is that is the norm with respect to the norm induced by the inner product. Induced by the inner product, that is called Hilbert space. An inner product space which is a Banach space with respect to the norm induced by a norm inner product space, that is inner product is called a Hilbert space. That is the simple definition. Induced the norm of inner product space is a Banach space that is called a Banach, that is called a Hilbert space. Now here the inner product space examples. First example and second example, third example, fourth example. N tuples of the real numbers, n tuples of the complex numbers, n tuples of the real numbers, n tuples of the complex numbers, and some other examples are also the set of all continued functions. Now, those examples are also preferable for Hilbert space examples. Okay. Now, some examples are considerable here. That is 10.4.2, 10.4.3. The field of the elements are real numbers and complex numbers are nothing but the Euclidean and unitary space. Euclidean means field of the elements are real numbers. So Euclidean norm and of these spaces, they are Hilbert spaces. Okay. Now, another one is just you have to see and refer. This example is also one of the definition. Linear isomorphism. Define linear isomorphism means X under inner product, Y under inner product. There are two norms here. There are induced by norm inner product X and Y. We two inner product over the same field K. So a linear map that is denoted by a transformation of the mapping is capital T defined from X to Y is a linear, it is said to be a linear isomorphism. A linear isomorphism, sometimes that is also called simple isomorphism. So given that transformation, given that mapping is when it is bijective and preserves inner product. When the bisective and preserve inner product Tx1 and Tx2 at the second norm equal to, so Tx1, Tx2 on the second norm of the part that equals to first norm of the inner product x1 and x2. So for all x1 and x2 belongs to inner product space of the part. Okay, now that is called linear isomorphism or simple isomorphism. That is the simple definition. Okay, please note the one of the important 11.3.3 completeness. This theorem is called completion theorem. Completion theorem. Just you have to see and refer the definition. For any inner product space, X under inner product, there is a Hilbert space H such that capital X can be embedded. X can be embedded into capital H as a dense subspace. Moreover, capital H means Hilbert space is unique map to linear isomorphism. Or if there is another Hilbert space H1 such that can be embedded into H1 is a dense subspace. So H and H1 are isomorphic. So that is called completion. H and H1 are both Hilbert spaces. H and H1 are isomorphic. That is called the completion. So this theorem is called completion theorem. Okay. Now this is one of the important theorem in Hilbert space 11.3.3. Please note down. This theorem is very important. That is the completion theorem. Please stay on the line. Please note down some other important here. Twelfth unit, bounded linear operators and inequalities. Please note down. Orthogonality. 11th unit and 12th unit, very important. Orthogonality, the Hilbert space definition and examples. And the 12th unit is orthogonality condition. Okay. See this one. Define orthogonality. Orthogonal of an inner product space. We are taking in any two vectors in an inner product space. So that is it read as inner product of x and y equal to 0. So here x and y both are orthogonal vectors. That is simply it's simple represented as x perpendicular y means yeah, that is the x is orthogonal to y means inner product of x and y equal to 0. That is called orthogonality definition. So that is the inner product of x and y equal to 0. So that is the orthogonal, x is orthogonal to y. Means that is simply inner product of x and y equal to 0. Next one, Pythagoras theorem. So let x and y be any two inner product space. So here one of the example, orthogonality cannot be reflexive here. So orthogonal relation is it equivalence relation. So x and y orthogonal, we dense x is perpendicular to y. That is also simple. Here it read as x perpendicular y or inner product of x and y equal to 0. So by IP3 condition, here 10 point inner product of xy equal to 0, y and x equal to 0. So according to this one, that is the usual basis and regular basis. X is 1 0 0 and y vector is 0 1 0, z vector is 0 0 1. Okay. Now according to this one, x perpendicular y and y perpendicular z in R cube. So there is also here x is not orthogonal to z, but here x and y equal to 0, y and z equal to 0. Now how to define in R cube of orthogonal vector, orthogonal definition? How to define in an usual base of orthogonality? So that is the x equal to, that is a simple question. Now you are taking any three usual basis of R cube. X is 1 0 0, y is 0 1 0, z is 0 0 1. Now you must find inner product x and y and z and x. Now if it is 0, now given the vectors are orthogonal. If it is not 0, that is not orthogonal vectors. So here x and y 0, y and z 0. That's why here x and y orthogonal vectors and y and z orthogonal vectors. But x and z not orthogonal vectors because that value is 1. Now, in the same manner, 12.3.2, this is also one of the important. Now, it referred as norm x plus y whole square equal to inner product of x plus y and x plus y. Now, it induced by the norm x and x and y and x, y and y. So this value is because y and x is orthogonal, x orthogonal y. So through the orthogonal vectors, x is orthogonal to y means that value is 0. So finally we are getting here x and y and y. So x and x means norm x square, y and y means norm y square. Now that is the definition of orthogonal. Okay, students. Now this is orthogonal and orthonormal sets. Now this is the 12.4.1. This is also one of the important definition. And according to the C, this proposition up to n consisting of the elements. So norm x1 plus x2 plus so on plus xn whole square equal to norm x1 square plus norm x2 plus square plus norm so on norm xn square. So that is also one of the important proposition. Okay, and each and every one is important here. 12.4.3. So any orthogonal set on an inner product space, it is a linearly independent set. Okay, students, already time is over. Anyhow, if you have any doubt, please contact us and personally. So there are so many theorems and successfully we have completed 12 units out of 18. That is not a joke. Especially you must watching through the a number of times you must watching in YouTube. Much more useful, especially in these sessions. Okay. Thank you, one and all. If you have any doubt, please contact us and personally. Okay. Once again, wish you all the best. And some other theorems in the remaining units are there. That is the Gram-Smith orthogonalization process and the projection theorem, and some other applications are also here. Okay, of course, you must thoroughly practice the first 12 units. Now you are getting the full-fledged marks out of 70 to 70. There is no doubt because that is the 70% successfully completion of this session. Okay, thank you one and all. Wish you all the best and wish you good luck.